So let us now talk about the moon. Lots of things to say about the moon. Well, the most important detail is, of course, that it is Earth's only natural satellite. Some things about it: diameter 3,474 kilometers, which is about 0.27 times Earth's diameter. Other things about it: that it has significantly smaller mass than the Earth, which means its gravity is about a tenth of what the Earth's gravity is. And it takes about 27.3 days to go around the Earth. It is about 384,000 kilometers from the Earth, and things don't need to travel very fast to get off the surface. So we're going to look at, in this presentation, the physical side of the moon. Like, what is it actually? What is it? Is it really made of cheese, or is it a very complex and interesting world full of rocks, valleys, mountains, and craters? Well, let's dive straight in. So the very first thing to look at is the size comparison relative to the Earth. They're both spheres, the moon and the Earth. The moon doesn't rotate as rapidly on its axis as the Earth does. It actually rotates on its axis about every 27 days, which is how long it takes to go around the Earth as well. As we'll see later, that leads to the same side of it always facing the Earth. About 0.27 times the diameter of the Earth, it makes it about the same size as Australia. Drawn to scale, it would look like this. You can see just less than 400,000 kilometers. It takes light about a quarter of a second to get to the moon from here. Now, because it rotates on its axis in 27 days, which is about the same amount of time as it takes to go around the Earth once, we find that it always presents the same face towards us. And the near side face that we can see is very familiar to us because we look at it every time we see the moon. And even though it might change because of the illumination, it is basically that same face that always faces us. The other side of the moon wasn't seen until spacecraft flew around the back and photographed it. Now here we've got the near side and the far side of the moon, and what you can see, they're quite different from each other. Now you may hear an expression, the dark side of the moon. Well, this could refer to one of two things. Either it's the unilluminated side, the part of the moon that is having the lunar nighttime. So that's the bit you can't see when you look up at the crescent moon. That's the dark side of the moon. But it's not normally meant to mean the unilluminated side. It's quite often meant to mean the reverse side, the far side of the moon. When the moon is full, then the dark side of the moon is the far side of the moon. But generally it doesn't stay dark, it's illuminated when the near side is in new moon phase. But we'll talk about lunar phases a little bit later. Here are most of the major features that you could hope to see with binoculars if you looked at the surface of the moon. You don't need to know all of the names of these. Also notice that for everything there's a Latin name and then there's an English name. You don't need to know that either. And knowing the names of some of them so that you can give examples is a really good idea. You can see here we've got in blue these mare, or seas as they're called. They're not really oceans, but we'll talk about those in a second. So the most obvious one here, Mare Imbrium, which is the sea of showers or rain. And we've got Mare Tranquillitatis, which is the sea of tranquility, which was made famous by the lunar landings. Also in orange here, you've got the major craters, the ones most visible. Perhaps the most visible of all is Tycho there in the southern hemisphere of the moon. Check that one out. Now, as we explore around the moon, we're going to look at some of these in greater detail. So first of all, let us look at those big dark patches on the moon, the Mare. Now, each one is called, well, a mare, and it's the Latin name for sea, in the same way that a mare maid is a sea maid. It's the word that we use for sea. Now, these are not really seas. Before we had a close look with good telescopes, we looked at it with basic telescopes, and they just looked featureless, like there was no craters on those areas. So people thought, well, maybe they were like the Earth's oceans, of which there are no features on the Earth's oceans as viewed from a great distance. We later found out that they were just smooth regions where lava from deep down inside the moon had leaked towards the surface and basically melted away any mountains or any other features that were visible. This then set, leaving a smooth surface onto which more recent asteroids came and collided and formed the odd crater here and there. So they're dark, and they form these great lava-filled basins. The sorts of rocks that we get in these, they're basalts, so those sorts of rocks that are formed from lava flows, and they're relatively recent in terms of the moon, between 3 and 3.5 billion years ago, and they represent the very last time that the moon's surface was molten. That basically the moon's surface started to form a crust and it started to set. Some of that was contorted and twisted into mountains and all sorts of things. But then when a large impact punctured through the crust, it allowed the lava basically to come back to the surface, and then it would freeze out in a smooth basalt surface that we call these the lunar mare. Now it was Galileo who first observed these. I mean, you can see the man in the moon. When you squint with your eyes, you can see a mottled pattern. But what is that mottled pattern? Well, it took Galileo, the first person to look at the moon through a telescope, to actually draw them and characterize them. He was also the first person to observe craters on the moon. And he published his diagrams, this one here, in the Sidereus Nuncius in 1610, the Sidereal Messenger, a book that changed astronomy forever. So roughly contemporary with Isaac Newton, just after Galileo, was this person, Giovanni Battista Riccioli. And what he did with a slightly better telescope was he drew the first moon maps, identifying where the craters were and also where the seas were. And so these moon maps, the very first time he was the first person to write the names of things, and he could just make up names. And so he thought really creatively about all these different oceans, gave them really fantastic names like the Sea of Tranquility or the Sea of Rains. Now this is one of his actual diagrams here. I just want to point out, can you see how there's the edge of the moon, top right and bottom left? It kind of extends beyond the circle. Well, we're going to explain that in a little. But first we need to just understand that this 17th century Jesuit astronomer was the person that gave the moon all these fancy names in the first place. So why did that map of the moon have like a little extra edge, top right and bottom left? It's because occasionally the moon shows a little bit more. You see, though it is tidally locked and always presenting the same face towards us, it rocks gently back and forwards over the period of one orbit to show us a little bit more, just a little bit of the edge around the side. And what we can do is we can pick it right. If it's tipped to the left, we can peek over the right-hand side. If it's tipped to the right, we can peek over the left-hand side. Time it right, we can actually map 59% of the entire moon's surface. This motion of the moon is called the libration of the moon. And basically, if we rewound the clock, we would find it exaggerate as we go back in time until eventually the moon was orbiting and rotating at different rates. And so at some point in the past, it wasn't tidally locked, but this libration of the moon is the leftover movement from that process. Now, forgive the picture on the left, that's actually me about 25 years ago, meeting the late, great Patrick Moore. Now, Patrick Moore was asked to map the moon in great detail with a telescope just before the moon landings. And one of the things that Patrick Moore noticed, though it had appeared in photographs before, he was the first person to point it out, Mare Orientale, there appeared to be a mare on the very edge of the moon that you could only see when the moon western limb was tilted more towards us because of the moon's libration. And so he basically discovered one of the major things about 300 years after they were named, a new one was found, Mare Orientale. It's round the back, and the word comes from like the Orient, which is the lands around on the other side of our planet. Here, this is the a mare that is around on the other side of the moon. Now, this is what it looks like. If you go fly around the back, it is a ginormous multi-ring crater, the very bottom of which is flooded by lava, which is now set. So you can see that this probably formed as one of the last major impacts when the moon was basically set. It's only at its deepest point that lava's managed to flood this crater, but it's still a lunar mare, and this picture, of course, taken by a spacecraft. So we didn't really know what the far side of the moon looked like until spacecraft 1959, in fact, when the Soviet spacecraft Luna 3 flew around the back of the moon and photographed it for the first time, discovering many things like the Tsiolkovsky crater. You can see it just there immediately behind the spacecraft. The photographs were very primitive compared to photographs we've taken today. We have now photographed it in high resolution with modern spacecraft. So if we're not talking about the lunar mare, then maybe we're talking about the lunar terrae, or the terra, or, as it's more often called, the lunar highlands. Everything that is not one of these basalt basins is actually an area that is higher than those basins, jagged, rugged mountains and craters, and always slightly older than those basalt mare. So this is mostly made out of anorthosite, a light-coloured igneous rock that set basically as the first surface of the moon as it became cooler and its liquid lava surface solidified into rock for the first time. Now, there's a lot more of it on the far side of the moon compared to the near side. Conditions to do with the tidal locking of the moon has meant that the lava has drawn more to this side, flooding some of those lower basins. But there's also the strong possibility that the moon's near side was impacted by lots and lots of ejecta from things that hit the Earth early on, giving the front side of the moon lots more impacts than the reverse side of that size. So the highlands of the moon contain highlands indeed. It contain mountain ranges, and if we go and have a look, these are the Lunar Apennine mountains, and they're around the edge of Lake Imbrium, or sorry, Mare Imbrium. And you can see that they are truly a mountain range, 5-kilometer high mountains. These are as high as Kilimanjaro, and they form a whole range, not formed by tectonic activities, but in this case, they are the edge of an ancient crater. Now here's something quite fun that we found on the moon: skylights, pits and tubes. So when the moon's surface was molten or partially molten, there were channels where hot running lava would pass along, perhaps just under the surface, channeling out a tube like an earthworm through the ground. And this lava tube exists, and there's probably several that are undiscovered that are still buried just underneath the surface. And just occasionally, they have broken through. So what we can see is a skylight, basically like a cave system whose opening is exposed to space. And indeed we can see where these rivers of lava flowed. They're called rilles. They're narrow depressions. They look kind of like rivers, but they squiggle around all over the lunar surface. And so when these mare flooded with basalts and it started to set, every now and again a fresh river of lava flooded across the surface, carving out a channel just like this as it flowed. So here is something quite different. This is a valley caused by tectonic movements of the earth. It's called Vallis Alpes, and what's happened here is contraction of the moon has actually pulled apart part of the highlands here. It's flooded with lava, but that pulling apart has continued and it's recracked the basalt layer underneath. So we've got like a valley in a valley due to the pulling apart, tectonic movements, if you like, movements of the whole crust as a whole, forming this valley. And you can see this with a small telescope to the top right there of Mare Imbrium and to the bottom left of the little tiny black crater Plato. Let's talk about the craters on the moon. This is the crater Copernicus. The moon is covered in craters like this, and so we're going to now look at all of the various different types and things that we can look for. Perhaps the most prominent are the 4 ray craters that are really visible on the front side, and none more so than Copernicus. It sits near the southern part of the moon. We don't see it on the left like this. We see it at the bottom, but this photograph's been reorientated. It's a crater, and it's quite recent as well, and it's caused a great big dusty splash of ejecta and material that stretches halfway across the moon. Anything hitting the moon now would not puncture through and create lava. It would just hit dry, solid dust and scatter it everywhere. There are 3 more craters like this, very close to each other, in the sort of right-hand side of the moon, Tycho, Kepler, and Aristarchus. In fact, there's all of them together. Impacts that have caused rays of material ejecta splashed across the surface of the moon. Now, these craters were caused by meteor impacts. So rocks from space have always been flying around, more in the past than there is now, and they've slowly been hoovered up by the planets and their moons. In this case, the moon has, for its entire history, been bombarded by rocks from space, and with no atmosphere to slow those rocks down, they collide with the surface with great force, forming and digging out a huge crater, some of them so energetic that they cause the actual material underneath to bounce up and form a central mountain in the middle of the crater. And mountains indeed they are. So this is the mountain at the middle of Copernicus, and you can see it casting a shadow over the crater floor. The mountain, or the central peak, is enormous, as high as the crater walls themselves. If you stood on the top of this mountain, you would look across a vast plain of the crater floor, and in the distance, the edges of the crater rising up. It's only the more recent craters of the time between about 3.5 and 3 billion years ago and modern day that actually have those peaks. The moon had to be solid when those impacts occurred for a peak to rise. If the moon was liquid or just partially solid, then what tended to happen was there was an impact that either punctured through the solid skin and exposing the lava underneath to space, or alternatively it punctured through and lava then seeped into the hole. And what this did is it eradicated any of the details of the crater floor, including any central peak that might have occurred. So this is Plato. It's a very good example of one. And what you can also see coming away from Plato on the top right is one of those rilles. So as Plato filled, it filled with lava until basically the lava then broke out and drained away somewhere else. So what is all of that ejecta that we see from those craters? Well, it's little bits of rock, some of which are quite big. In fact, if we look at nearly any part of the moon's surface, it is absolutely scattered with ejecta. From all of the impacts that have ever happened on the moon, all of that ejecta is still littered around all over the surface, some of it a bit more buried than others. But when we visited the moon, we found huge jagged boulders that had been thrown out from an impact event from billions of years ago. Now, impacts of the moon have happened in all shapes and sizes. Some of them have been truly ginormous early on in the history of the moon, but every single day the moon gets hit by tiny meteors. Every time this happens, it breaks the rocks, it flicks up little tiny bits of molten rock into the air that sets as like a kind of glass that sets again as a solid and falls back on the ground as lunar dust. This regolith of it, as it's called, is millions or billions of years of tiny little impacts pulverizing the lunar surface, and now there's as much as 20 meters thick dust. If you stand on the moon, you sort of settle into it, and this is why there are now footprints on the moon. It causes problems in some ways because it gets all over the spacesuits and all over the vehicles when they land on the moon, and then when they go back inside a space capsule to fly back to Earth, when the gravity goes to zero, it all becomes airborne and you're breathing in moon dust, which is not good. Now, the imprints, the footprints from the astronauts in the lunar dust isn't going to be disturbed now for billions of years. So after nearly all of the Earth's rocks are reprocessed that show any sign that human beings ever existed on the Earth, after all of that has gone, there will still be footprints on the moon. The rate at which the lunar surface is now being modified is on the billion-year timescale.